All right, so hopefully you guys had a great holiday. I know I did. I enjoyed it. In the last class, at the end of the last class, a student, I forget who it was, but somebody asked about how pixels work. And we talked a little bit about that after class, but I said I would say a little bit more about it today. So I'm hoping I can get to that. The more I thought about it, the more excited I got, because it's actually a good way to tie some of these concepts together when we talk about numbers and codes. So I really thought about that, and I was like, man, no, I don't know why I never thought about talking about pixels, because that's something I think you guys can relate to. So today I want to do two things. I want to we started talking about number systems. We looked at the binary number system, and then we extended that to any old number system. And the main ones we worry ourselves with, or we look at in digital systems, is we look at the of course binary, because that's machine language, but also there's a number system based on base 8 called octal, and another based on the number 16. That's called hex or hexadecimal. Base 8 because, as you know, if I have four bits, that's a nibble. 2 nibbles is a byte, or 8 bits is a byte. So typically with digital devices like a PC or cell phone, the smallest piece of information that you can manipulate, you can process, you can move around is a byte, 8 bits. PLCs are a little different because you can actually address an individual bit. But for most digital devices, it's a byte, a group of 8 bits. And so we talked about the octal number system based on 8, and then the hexadecimal number system based on 16 bits, 2 bytes. That's a natural for PLCs, because for a lot of PLCs where they have 16 16 connection points on the input module or output module. 16 is a natural number, it's 2 bytes, and so often we'll use a word size of 2 bytes, which means that base 16 is important. So we looked at both of those. We did practice going from both number systems, octal and hex, to decimal and vice versa. So you should be familiar with that. What I want to talk about today is the other part of the digital equations. We talked about numbers. Numbers have place values. I want to talk about digital codes. Digital codes. So code, for the most part, codes, you can distinguish a piece of data code-wise by the sequence of bits listed. Now, some codes do have, you can't see me now because I have my camera off, but kind of I'm doing air quote, a type of a place value. But for the most part, codes, you can just distinguish one code from another by the sequence of bits. So we're going to look at one common code used called BCD. There's another common code used called ASCII, and then we'll talk about a code that's designed to minimize errors called gray code. We'll actually use gray code later in the semester. So that's the agenda for today. And then if we have enough time, I'd like to say a little bit about the pixel question that somebody asked about on Friday. And if not, we'll get to that on Friday. I did not have a chance to update my Canvas, so I didn't get a chance to go in and do any grading or looking at anything that you guys might have uploaded. I will take care of that today, but sometime today I'll get in and I'll do some grading and get caught up on that. But I think I don't think I turned on the module for this week, so I'll have to do that. So I'll make sure that's all taken care of sometime today. What you're looking at on your screen right now is the first type of code that I want to talk about. This is called ASCII code. ASCII code. I forget ASCII. I think it stands for American Standard Code for Information Interchange. I believe that's what it is. American Standard Code for Information Interchange. You can look it up, but I'm pretty sure that's what that stands for. What's important for us, though, is not what the letters mean, but what is this ASCII code? Well, basically, remember, anything you put into a digital device goes in as ones or zeros. So all we can do is represent anything on the outside of the digital device as a 1 or 0, or a group of ones and zeros. So how would I represent, say, letters on the keyboard. Or even bigger than that, how would I represent any character on the keyboard? So what you're looking at now is called ASCII code, and what it is the code used to store any character on the keyboard. So you might look at these, and well, if you just kind of dig in here, you'll look. Some of the characters you can actually print out. Some of them are printable characters. So like over here, you have your uppercase alphabet letters A through Z. And over here, you have your lowercase alphabet letters A through Z. So those are all separate letters on the keyboard. And you'll notice also that each one of these has a binary code associated with it. So let's say that on your keyboard, you type, well, let's say you type the letter A. If you type the letter A, what's echoed to your keyboard, now when I say A, I mean the uppercase A. Say you type an uppercase letter A. What's reflected to the keyboard is that uppercase letter A, but what's actually stored in the system is this binary code right here. So this is the ASCII code for uppercase A. Over here is the ASCII code for a lowercase a. And you'll see that there's other characters, like the, I don't know, maybe the percent sign here. Every character on the keyboard has a binary representation that's unique to that character. Now, some of these characters are printable, like the uppercase A and the lowercase a, but over here, for example, you'll see like right here, BEL, that stands for bell, and that bell sound, the ding that you hear when you hit a key, and maybe, I don't know, when you hear the ding sound you hear when you hit a key, maybe you hit a key and it's an error key, or you hear the little beep sound out of your computer. Well, that's actually has a binary code. It's a non-printable character, but it has a binary code. So all of this list over here are all the printable and non-printable characters. Now, if you look over here, you'll see these numbers 0 through 9. And for each number, like for the number 1, look at the number 1 over here. It's not the binary number 1, because the binary number 1 would have 7 leading zeros and just the 1 in the rightmost bit. Well, the binary number 2 would not look like this. The binary number 2 would just have a 0, a 1, and all the other leading bits would be zeros. So these are not actual numbers, these are characters. It's the character 0, the character 1, all the way up to the character 9. So these are printable characters, but you couldn't do math with them, is what I'm saying. So I have the printable characters. When you hit on your keyboard number 7, then what you're hitting on the keyboard, let's say you're typing a letter, and maybe you're making a list 1 through 7. When you hit the number 7, then what's actually stored is this digital code right here for 7. Now you might think to yourself, well, hold on a second, Singleton. I can turn my computer keyboard into a calculator, and I can do math. I can actually do math on the computer. And right, you can do math, but at that point, you're not using the ASCII values for those symbols. When you type in, let's say you do 2 times 3, when you type in that 2, it is not the ASCII value for 2, it's the actual binary weighted value for 2. So what you have here is a list of every printable and non-printable character on the keyboard. Now, the other thing to note here is that as you know, as we said many times, anything that goes into a digital device goes into machine language. It goes in as zeros or ones. And that zeros and ones can either be a code, as we're looking at now, or it could be a number that has place value. But you also see that each of these ASCII values has an octal value and it has a hex value. So if I look at that octal value and the hex value, what you want to remember is that no matter what we as humans, what we see or how we think about it, what actually goes into the machine is zeros and ones. So like here, for the uppercase A again, we'll pick on that one. The hex value for it is 41. The octal value for it is 101. So that would be a 101 base 8 or 41 base 16. Or if you convert it to decimal, it would be a 65 base 10. So however you want to think about it, the hex, the decimal, the octal, that's just for us. It's for convenience of humans. What actually goes into the machine, no matter, let's say you're writing a program. If you know a programming language, it's customary in the programming language. Let's say you wanted to list all the letters from A to Z, upper and lowercase in the programming language. It'll be really, really easy to do because you can just write a simple loop and you can count from 0 over here in decimal. You can count from 0 all the way over here to 127 and have the computer print out the actual ASCII character that's mapped to that particular decimal value. So you can print the number 0 to 1 or every printable character in a computer program. You can do that pretty easy. But remember, no matter what you have in that program, say you tell it to print decimal number 65, it's going to print an uppercase A. What's actually stored in the machine is this number right here for A. The only thing that digital device can store is binary, machine language. So all the other number systems we talked about, base 10, we talked about hex, we talked about octal, those three number systems are just for us as humans. We look at those. Sometimes you'll see address lines numbered in octal or hex. You might see memory locations numbered in octal or hex. But in the actual machine, those are all done in binary or machine language. So here is the first code, ASCII. There's something else I want to talk about. Let me go away. Well, first of all, does anybody have any question over ASCII code? Let me see if you have any questions. And then I want to talk about something else. We'll move away from the code. I want to show you something, and then we'll go back to the PowerPoint. Anybody have any questions on ASCII? Now, you might wonder, I have a comment. You may not have a question, but well, what about, so the keyboard, this shows all the uppercase and lowercase letters in the English alphabet, right? What about, you have the Arabic, or you have Mandarin Chinese. You have these other languages. What happens there? We actually have, and I forget the name of it, but it's kind of an extended code, so that basically almost all the languages on the planet, basically almost all the known languages on the planet, will have some kind of extended code and a extended table similar to this one that represents all the, I shouldn't say all, but many of the popular languages is used around the earth. So that's ASCII code. I want to show you this though. So this turns out to be pretty important. So you might recognize this device. It's called some people call it a LED display. LED, the L stands for light, the E stands for emitting, the D stands for diode. So you guys are probably familiar with LEDs, but the LED, light emitting diode, a diode is an electronic device. It's a solid state device. Now remember, solid state means it's just made out of a solid crystal, typically silicon. It's a solid state device that allows current to flow one way and not the other way. So think of it as a one-way valve for electricity. It turns out that a byproduct of this thing called a diode is that it emits light. And not only does it emit light, but it does so very efficiently. It's not like a regular light bulb that uses a gas or filament. LEDs are solid state devices, and they're very, very, very efficient. So much so, they have like 50 times the life of a regular incandescent bulb. They don't use a lot of power, and they don't have any parts that move, so they're very, very durable. So the 7-segment display is actually 7 elongated LEDs on the chip. And so you have them here, they're labeled. You'll see they're labeled with letters of the alphabet A through G. So if you count, there's 7 segments of the LED. And so they call it a 7-segment display. And this particular one has a decimal point. Well, the idea is that you can light up certain LEDs on this chip and get any of the digits 0 through 9. For example, if you look over here on the left, now they got these switches. It's not really done with switches, but this is just so you can think about it. They got these switches here. Now this one has a decimal point, so there's a switch for the decimal point, but just ignore that for right now. So you got these switches A through G right here. And if you close switch A, you close this circuit, then current can flow this way out to ground, and it'll light up this segment right here. But if I close segment A, B, and C together and leave all the other ones open, then what you'll have is the number 7. This is lit, this is lit, and this is lit, the number 7. If I close switch A, B, C, D, E, F, then what you'll have is a 0. So you can see by closing certain switches, and again, this is not really done by switches. This is actually controlled with another chip or transistors, but just for ease of understanding, you can close any certain switches, and you can actually get any of the digits, the number digits 0 through 9. If I close all switches, then I'll get the number 8, right? I have an 8 there. Okay, so keep that in mind because we'll come back to this twice. We'll come back to it today. We'll talk about the type of code that we use to control one of these, and then one of your lab projects, I believe, when you it's either a lab or a design project you'll do later in the semester, makes use of this. So we'll come back to this 7-segment display. So anybody have any questions over the 7-segment display? Just kind of get a basic understanding of how it works. Oh, wait a minute, I see. Oh, okay, somebody was saying that they could hear me. All right, so let's go into the PowerPoint for today, and we'll look at some other code. So let me see here, PowerPoint. All right. So we've already talked about ASCII. I want to talk about BCD. BCD stands for binary coded decimal. We'll talk about gray code. And parity, I won't say a whole lot about parity because I think one of your homework assignments actually deals with parity. I'll kind of mention what it is, but I'll let you do research on how it actually works. So let's start talking about the BCD number system. So the B, the C, and the D, what does that stand for? BCD stands for binary coded decimal. Binary coded decimal. Now, if you actually have a 3-ring binder and you're printing these slides out on the note pages, 3 slides to a note page, and you're putting that in your binder, here's one of the ones you want to mark down, because on one of your quizzes or exams or at some point, I asked what the B, the C, and the D stands for. So BCD stands for binary coded decimal. Binary coded decimal. Why do we have BCD? Well, it turns out that basically you're going to use BCD anytime you have a digital device that requires a number input or output from a device like, say you have a digital readout. You want to have something read the numbers 0 through 9 or some combination of digits. Or you have something called a thumb wheel. You can actually, maybe like a lock, electronic lock, you can actually dial numbers into a system. Well, when you have numbers inputted or outputted that way, then typically we don't use a weighted number system. We use BCD, binary coded decimal. The reason is when you display a digit, you can only display the digits 0 through 9. And once you get past 9, what happens was, we start to repeat digits. So I can count from 0 through 9. So if I have just one LED, one of those 7-segment displays that I just showed you, the only thing we can count on that one chip is 0 through 9. If I have 2 of them side by side, one can go 0 through 9 and the other can go 0 through 9. So now I can count from 0 through 99. If I have a third one, I can go from 0 to 999. So you get the picture for each individual chip, each individual 7-segment display. I can only light up one number at a time. And so we don't want to use a weighted system. I need some kind of system that just basically allows me to light up the digits 0 through 9. And so BCD, binary coded decimal, is the system that we use to do that. And so the big thing here for BCD is this bullet point right here. To understand that in BCD, what you do is you use 4 bits. You use 4 bits to represent each of the decimal digits 0 through 9. Now remember, you'll have a 7-segment display, and it can display 0 through 9. So that's like 4 bits that can display 0 through 9. If I had another 7-segment display, I can feed it with 4 bits, again, that can display 0 through 9, but now I can count from 0, 0 all the way up to 99. Okay, so let me compare it on this chart and it'll make sense to you. So typically, in decimal, we can count from 0 to 15. So I'm showing you the count over here, 0 through 15. In binary, you can do the same thing. Binary is a weighted number system, so I can write the binary equivalent for every decimal number that I have over here on the left. So like for the number 1, I got just 1 bit. For the decimal number 2, I got a 1, 0 base 2. For the decimal number 3, I got a 1, 1. That's in our 8421 code. That's a 2 and a 1. 1, 1 base 2 is a 3 base 10. And I can just keep going, counting like that. But notice what happens when I go over to these, the count where I have 2 digits, like right here. 10 in decimal is a 1 and a 0, right? It's a 1 and a 0. Well, in binary, a 10 base 10 is a 1, 0, 1, 0 base 2. If I do my 8421 code, this is a 8, and that's a 2. 8 and 2 is 10. So a 10 in base 10 is a 1, 0, 1, 0 in binary. Now you'll notice if you look at the BCD, basically the BCD up till this point right here, from 0 through 7, you see that the binary and the BCD are exactly the same. Actually, all the way down to 9, they're exactly the same, except for, you'll notice that on purpose, we're using 4 bits to represent the BCD. So over here, I can just use a 0, or I can just use a 1 to represent a binary 1 or 0. In BCD, if you want to represent that 0, you'd have to use 4 zeros together, a half a byte. If you want to represent that 1, again, you use 4. You got to put in the leading zeros. It's got to be 4 members on that particular nibble, that half a byte. Well, where it differs, where BCD and binary differs, is when I get down here to number 10. Because what you want to do is you want to use 4 bits for every decimal digit. So notice for like the 1, let me erase this. For the number 1, for this 1, these 4 bits represent the number 1. And then for this 0 right here, these 4 bits represent the 0. Or go down here to 12, I got a 1. So I'm going to represent that 1 using 4 bits. And I got a 2. And I'm going to represent that 2 using 4 bits. So over here, here's the binary for 12. Binary for 12. If I use my 8421 code, I got an 8 and a 4, that's 12. So in binary, a 12 is 1, 1, 0, 0 base 2. But in BCD, that 12 would be a 0, 0, 0, 1, 0, 0, 1, 0. And again, the reason is this 4 bits right here will light up one 7-segment display. That will give you a 0 through 9 for the leftmost digit. And then this set before right here will light up the second 7-segment display. And it too can display the digits 0 through 9. So I can start out counting at 00 and go all the way up to 99. And with 277 displays, I can count up to 99. So the difference between binary and BCD is binary is a weighted system. BCD is kind of a weighted system, but it's different because what you have to do is use 4 bits to express each single decimal digit. And so here's an example of a decimal number that I want to express using BCD. So I will show 7, and I got to express that using 4 bits. So I got a 4, a 2, and a 1. That's 7. I want to use the 8, express that in 4 bits. So I have an 8, is a 1, 0, 0, 0. That's an 8 in binary, a 6. I express each one of these using 4 binary digits, and I put them all together to get this one long BCD number. And then each block right here that you see, each one of these blocks, this one right here, can light up a 7-segment display. And it can go 0 through 9, so I can display the 7. This one can light up its own 7-segment display. That 7-segment display is going to have, the decoder for it's going to have 4 input wires. And it will display 0 through 9. Now you'll notice over here, we didn't subscript this with a base 2 because it's not base 2. It's not a weighted number system. It's not the binary weighted number system. It's an actual code that we put together. We put these individual binary numbers together to get the BCD code. So you can't subscript that with a base 2. If you put these zeros or ones on the board, you walk out the room, I put this long list of zeros and ones on the board, then you walk back in, you don't know if it's binary or you don't know if it's some other kind of code. So now we got to specify what we're using. And to distinguish this from just normal weighted binary, you would subscript this not with a base 2, you would subscript it with a BCD. And so if this is BCD code, your subscript should not be base 2, it should be BCD. Here on the slide, they use an uppercase BCD, but when you subscript it, you can do it either way. You can have uppercase or lowercase for the BCD, that doesn't matter. Okay, so if I want to use this in some kind of a system, here's an example of a system where you might use BCD. So you'll notice, first of all, notice over here on the left, we have this input device. So you have something, they have called a thumb wheel. A thumb wheel is like, kind of works like those padlocks with the wheel on it. It has the digits 0 through 9. You can use your thumb to set the code, to move the numbers up and down. So imagine something like that, a thumb wheel, or you have some kind of dial where you can dial these digits in. So you dial in a 6, you dial in a 4, you dial in a 1, you dial in a 9. So each individual number has to be converted or represented in BCD. So this input device would actually output, either the input device will actually output to the input module BCD, or it'll be the job of the input module to change this to BCD. Some kind of way we have to represent each individual digit as a BCD number. And so that BCD number comes into our input module, or the input module will convert it to BCD. And then once we get into the actual PLC, remember the PLC only understands binary. Even though BCD is zeros and ones, that BCD is not machine language. It's not binary. So we got to convert it from BCD to binary. So here we have this circuitry or this device that does a BCD to binary conversion. And once it's in machine language, normal binary, only at that point can the processor do something with it. So now we can process it. We can do whatever your program is going to do to the BCD. And then let's say at that point we want to display digits again. We want to go from our thumb wheel. We want to have some kind of output, right? Maybe I have a 7-segment display and I want to display the number 1765. And so over here on the decimal readout, I got a 1, 2, 3. I got four numbers here. Each one of these numbers here is a 7-segment display, and it does not understand weighted binary. It only understands BCD. So what I got to do, if I know that I want to, whatever this digital readout over here is on the left, if I know I want to connect that to my digital device, then the PLC or digital device has to go from binary back to BCD. And the output module will receive the BCD, and then it will display the digital readout 1765. So binary coded decimal, BCD, normally that's used when you want to input separate digits of a decimal number, or you want to output separate digits of a decimal number. And when you're outputting separate digits of a decimal number, typically you're going to use something called a LED, 7-segment display, or there's LCD, which is called liquid crystal display, but even the LCD is 7 segments. So BCD is the second code that's important for us to wrap our minds around. So far we got ASCII code. There is a 8-bit code, binary code, to represent all printable and non-printable characters on your keyboard. And BCD, binary coded decimal, we use that to display the single digits 0 through 9 when I want to display those digits so that I can read them with a digital readout, or if I want to enter each digit independently using the thumb wheel or some other kind of input device that allows me to enter individual digits. Then I want to use binary coded decimal. So we got ASCII and we got binary coded decimal. Anybody have any questions before I move on? The next code, and this is actually the last one we'll talk about, the next code is called gray code. Now, gray code, we're actually going to use gray code as a tool later on in the semester. We're going to use gray code as a tool to help us to reduce or to minimize logic functions. I don't want to get into that right now, but basically, gray code is called an error minimizing code. And we'll talk about why it's called an error minimizing code after we take a look at it. A couple points on this slide here. It is a code that does not use position weighting, so it does not use place value. So you can see that BCD kind of used place value. It used place value, but you had to use 4 bits for each separate decimal digit. And within each of those 4, we use place value. So some codes do use place value of some sort, but here gray code does not use place value. They're not weighted. It only relies on the bit sequence that we talked about earlier. So let's compare gray code to binary. So over here, we got binary, we're counting in binary. We're counting as we go down the list. And then over here on the left, you'll see the gray code equivalent. So we start out at 0. So the gray code and binary are exactly alike as I go down. But look right here what happens. They're different right here. Matter of fact, look right here. So right here, a 1, 1, 1 base 2, that's a 7. And a 1, 0, 0, 0, that's an 8. So when I change from 7 to 8, look over here at the gray code. The codes are different. So to represent that 7, it's a 0, 1, 0, 0. Remember, we're not using place value here. We're not using position weighting. It's just this sequence of bits on the left represents the binary number on the right. This sequence of bits right here represents that 8 in binary on the right. You might say, all right, why would you map these two? I mean, both the left and the right column, both the gray code and the binary are 4-bit numbers. Why would I create this other system, this gray code system, and I map these numbers to the binary? That's just, why would I do that? Well, the special feature about a gray code that you don't have with other codes, you can really see it right here. Notice that when you transition from 7 to 8, every bit changes. When I'm up here and I go from 0 in binary to 1, the only bit that changes is that least significant bit right here. And when I go from 1 to 2, again, only 1 bit changes. When I go from 2 to 3, I got to change. This bit stays the same, but then this bit changes. So as I go down the list, I'm counting in binary. I get more and more and more bits that changes until I get down here to 7. There's a bit change, right? When I go from 7, a binary 7 to a binary 8, each bit has to change. Every 0, the 0 becomes a 1, and every 1 becomes a 0. I got to change 4 whole bits. Well, remember, we have machines doing this for us. We have machines and we have circuitry changing bits. And it turns out that the more often you have to change bits, or I should say the more bits that change in any given time, the more the likelihood that some error might be introduced into the system. And when I say that, there's a lot of ways errors can be introduced into the system. There might be a voltage pulse. There might be some kind of electromagnetic noise. There's a whole host of reasons we can talk about that would introduce noise into the system that could affect these bits. Now remember, these bits are not just sitting there. I mean, they may be held in memory on the register, but typically in your computer, your phone, your digital device, these bits are going in and out of memory, the microprocessor is moving these bits around. It's making those waveforms that we talked about and storing the waveforms as zeros and ones if it's got a hold, the number or the data. So these ones and zeros they're dynamic, they're not static. And when you're moving these around, the likelihood that a single bit, I mean, think about it. If you're moving kilobytes, the likelihood that a single bit could accidentally get switched over, or several bits get switched from a 0 to a 1 or vice versa, that likelihood increases with the complexity of the system. So with gray code, if you code a binary number, or if you code say alphanumeric data in gray code, as you go down, you'll notice only 1 bit changes at a time. So even down here in binary, when I went from a 7 base 2 to an 8 base 2, I had to change 4 bits. But if I look at the gray code representation of 7 and the gray code representation of 8, as you go down this list over here, only 1 bit changes at a time. So if you had some reason to move bits around, I shouldn't say the most, one of the most secure ways to do it that would result in the least likely amount of error when you're moving these bits around is to use gray code. And it's just one of many codes that we could talk about. So that's the reason why they call gray code an error minimizing code. So if you have a need, if you have a reason to move, let's say you got some kind of mission critical data, maybe you're working for the Pentagon and you're designing a new plane, and you know when you guys do that CAD stuff and all that stuff that you learn, and you want to move bits around, and it's mission critical information, you might want to code it in gray code and move it and then convert it back to binary, because there's least likely to be a change in a bit or error introduced to the system. So that is gray code. Anybody have any questions over gray code? We already talked about ASCII code, so I don't really have a whole lot to say about ASCII. You can read this slide and you know, mark it. Just know that any symbol on the keyboard is not, we don't use a weighted number system to represent symbols on the keyboard. Printable and non-printable characters have their own unique ASCII value, a set of 8 bits to represent each upper lowercase letter on the keyboard, and every symbol, printable and non-printable, has a unique set of codes called ASCII code, 1 byte. Each one is 1 byte. And then the point of this next one is that we have circuitry. You might say, well, how do I go from BCD to just regular binary, or vice versa? Or how do I go from binary to decimal? We have these actual chips, and everything we're talking about, these chips, everything is based off of and or logic. That's the fascinating part of this for me, that you start with those three basic logical functions. You have AND logic, OR logic, and NOT logic, and everything we've talked about we talked about binary addition. That's all done with AND OR logic. You can just take those chips and actually make an adder off of those basic chips. Here you have a decoder. You can just, with AND OR logic, there's actually circuits that will encode or decode these codes or these number systems that we've been talking about. So it's all pretty fascinating if you get into the details of it. So the point of this slide is we don't do any of this by hand. There's circuitry either in the input module, in the PLC, or at some point there's these encoders and decoders that does all this work for us. We don't have to do anything by hand. I don't really have anything to say about this. You can read that if you want to. I will say one thing about this. So in this slide, it talks about, now remember guys, these zeros and ones are not just floating around in your cell phone. They have to, they're either, if they're being held, they're held in something called a register. Think of a register as just a array, like a Excel spreadsheet. And each row in the Excel spreadsheet, for us, is one word, which is 16 bits. And in each cell, I can put a 1 or a 0. So we said a word size can be any size. It's machine dependent. We're only using 16 in here because, well, your simulation software has 16 connection points. It has a 16-bit register. But here, since I'm using a 16-bit word, you'll notice that this range right here, this number, they give you this range that you can count. What you would do is you take 2 to the 16th power. And that is the maximum decimal value you can count using the particular word size. So we got, what I'm saying is, if we have a register that's 16 bits, and each bit is a 1, we set each bit high, then the highest value I can count to is 2 to the 16th, whatever that is. Now, over here it says 32,767. Now, I don't have a calculator. Because somebody tell me, what is 2 raised to the 16th power? Somebody figure that out for me real quick. 2 to the 16th.
65,536.
65,536. Okay, so now take that number and divide by 2. Tell me what you get.
32,768.
32,768. So that would be the highest value that we can count, the highest number we can count to using a 16-bit register is 65,536. If I want to count higher, I'd have to get a bigger register or take several registers and put together. We might say, okay, well, why do they have on the sheet here 32,767? Well, it's because they decided they wanted to use negative values too. So if we want to count, we can go 1, 2, 3, all the way up to 65,536. Or if I want to take the integers, I want to involve integers, so now I'm going to have negative and positive values. So now I can go, I got to split that number in half. The 65,536, I got to split that in half. And he said you got 32,678. He said when he took the number 65,536 and divided it in half, he got 32,678. Well, if you notice on here, that's not what they have. On here, he has 32,767. And the reason he has a 7 here, not an 8, is we start counting from 0. Remember, in digital, we don't go 1, 2, 3, 4, all the way up to 32,767. We go 0, 1, 2, 3. So now I can only, I'll count 32,767. I'm starting at 0, it's 767. If I start at 1, it's 768. So that's not, don't even write that down. It's not a big deal. But I know by some of the questions you guys ask, some of you really want to know what's going on inside your machine, and that's where it gets interesting when you want to think about the word sizes and what these registers are doing and all of that. So the other one, this other PowerPoint slide, I'm not going to say anything about the parity. Basically, parity is like this. When you when you send information, let's say you send some information over the internet. You send it from my computer to your computer. How do you know the message that you sent is what my computer received? It doesn't have to be a computer. It can be a cell phone. I'm taking a drone class. I'm learning to fly a drone, and the way the controller communicates with the actual aircraft, it uses the analog signal, but it digitizes it. And how do I know the bits sent from the transmitter is what the receiver on the drone receives? How do I know that? So how you know what you received is what was sent? Well, parity deals with that. So that's all I'm going to say about parity, and I'm going to let you guys with this homework. I don't know if it's the next homework or the one after. You'll have to do a little bit of research into parity, and you'll learn about that yourself. So I'm not going to say anything about parity. Now, I did want to say, I don't know how much time I have. Let me see. First of all, let me turn the camera on. I never did that. I want to say a little bit about the pixel thing because somebody asked about it. I still got 5 minutes. I may go over, but let me just do this real quick. And guys, if you have to, if you got to sign off for another class or you got to go to work or something, go ahead because I'm not going to test you over this. I'm not going to. This is all just extra stuff to help you understand kind of what's going on in the machine. So if you have to go, you can go. I will post a video of this. So if you want to go back and watch it, you can do that. Let me get off of this, and I'm going to try to share something with you, but I'm not really good at this Zoom. This is not Zoom. Whatever this program is, I'm not good with this thing. So I'm hoping I can share something. But let me just talk about pixels real fast. Before I do that, anybody have any questions or comments over anything I've talked about today? Any questions? All right, let's talk about pixels. So remember what we said about week one. We talked about any kind of information that you want to get into a computer. And for us in here, a computer is anything that contains a microprocessor. So that's your cell phone, your microwave oven, if you can program it. If you can program your refrigerator, that refrigerator is a computer. All it can understand is zeros and ones. So if you take a picture, if you make a recording of a sound, if you shoot a video, if you look inside the chip, inside the device, it all looks the same. If you can see inside of there, it's all zeros and ones, and you couldn't tell what was what. But if you want to make a picture, though, let's say a color picture, then a pixel is like, think of it as a point. It's a point. Just a point. So a pixel is a point. And that pixel can take on any color. So if I wanted to show a picture, a color picture on your computer screen, even though it looks like just a bunch of continuous colors, there's really a bunch of almost microscopic, I want to call them little LEDs in there, all the way across your flat panel TV screen or your computer screen. And you can light all these up, and it looks like a line. If you're far away from it, it looks like a line. We talk about the resolution. They look at how many of these little LED lights or how many of these little pixels, how many of those points you have in 1 inch. The more pixels per inch you have, the higher the resolution. So if I use, instead of maybe I have 25 lines here, 25 dots here, if I use 50 dots to represent each point here, then the line's going to look a lot crisper. The picture I make or compose with that lines using 50 pixels per inch, it's going to look a lot sharper, a lot cleaner than if I'm using 25. The resolution is higher. But remember what we said when we talked about resolution. For every point, I got to use a code for every point to store. I got to use zeros and ones to store every point. So the higher the resolution, the more codes I got to use. That means it's going to take longer to move those bits around. So there's a trade-off, is my point. But interestingly, a pixel is not just a set of a single code. It's actually 3 codes. And the code that they use called RGB. So it's called RGB code, and the R stands for red, the G stands for green, and the B, of course, stands for blue. So let's say I had all those pixels on that to make up a line. Let's just look at one of them. If I look at one pixel, and I want to store the color for that pixel, it's going to take 3 8-bit words. I need to store the value for red. I need to store the value for green. I need to store the value for blue. And what is this thing about red, green, blue? Well, I really don't know. You guys, I probably should know this, but you remember how you guys know when you're in like, I don't know, kindergarten or first grade, you can mix colors. I think you can take like yellow and yellow and red or something. Make what is it? I don't know. I don't know my colors, but you know what I'm talking about. You can take two colors and make a third. And if you know, like people in the art world, they know that they can take red and they know what color it'll make. I don't remember what that stuff. But I do know that you can do the same thing with these digital primary colors. You can take red, green, and blue, and depending on the brightness of each, when you mix them together, you can get almost any color you want in the rainbow. And so with this pixel, instead of having one set of binary values that they store, it takes for each dot, each pixel, and this is a perfect point. For each pixel, it takes 3 8-bit words. So I need to represent the color red, and they're going to use 8 bits for that. I need to store green, 8 bits for green. 8 bits for blue. That's just for one pixel. So on your computer screen, on your cell phone screen, you may have 1,000,000 pixels. So I mean, the number of bits is just unwildly. So this is a good example of the trade-off. The fact that we got to use so many. Now, if I just wanted black and white, this would be a lot easier for me to make a picture. But that's we don't. There's no pleasure in that, right? So each pixel is a certain amount of red, blue, and green, and I can adjust the value of the brightness of the red, the blue, the green to mix those to get any color I want. Now, if I use 8 bits for red, 8 bits for green, 8 bits for let's see what this will be. Now, let's change this to hex. So if I use this in hex, now remember, typically they show this. Because who can remember all these ones and zeros? But you can remember, people that work with this every day, they remember the hex values. Again, this is a perfect example of, even though we're doing stuff in binary or machine language, we like to think in hex or octal because it's easier to remember. So if I use 8 bits for red, 8 bits for green, 8 bits for blue, 1, 2, 3, 4, 5, 6, 7, 8. Let's convert. The smallest amount of red I can have is this. 1, 2, 3, 4, 5, 6, 7, 8. So these can all be zeros, or these can all be ones. I can have a 1, 1, 1, 1, 1, 1, 1, 1. That's the greatest amount of red I can have. And I can do the same for the green and the blue. But we don't want to look at all these zeros and ones. What we really want to look at is to think about it in hex. So we can convert this to hex. Remember, when you go to hex, what you do is you divide it up into 4 bits. I'm going to go 1, 2, 3, 4. And I convert each one of those. I get the binary weight of each one of these. So remember our 8, 4, 2, 1 code. And these are all ones. So 1, 1, 1, 1. I got an 8, a 4 is 12, a 2, 14, and a 1. That's 15. That's a 15. So a 1, 1, 1, 1 base 2 is a 15 base 10. But remember, in hex, how hex works, we go 0 through 9. It's the same as decimal. But when I go from 10, 11, 12, 13, 14, 15, in hex, I use an alphabet, A, B, C. 15 would be F. So if you convert a 1111 from binary to hex, then the hex value of it would be a F, and over here would be a F. So instead of looking at this in binary, what you want to say is the color red, I can go from a 0, 0, base 16 all the way up to a F, F, base 16. So that's a lot easier to look at than this. So by adjusting these numbers right here, I get different brightnesses or different amounts of red, green, and blue, and I can have any color I want. So each individual pixel is able to actually display certain brightnesses of those colors. There's a diode called a tridiode that you can look it up on YouTube or the internet. There's an actual diode. You ever seen people, they'll have an LED and they can do a light show. That LED can produce any color light. You've probably seen those banners. They're LED banners. Well, what that is a single LED, but it has 3 elements in it. 1 element for red, 1 for blue, 1 for green. And by varying the intensity of the red, the blue, and the green, you can get any color you want. And so you're able to get colors of LED light, really millions of colors. But what I wanted to show you, let me try to share the screen with you because there's this application that kind of shows what I'm saying, but let me see if I can figure out how to do this. If I don't do it the correct way, I'll just give you the website. So I think I want to go to, wait a minute, hold on a second. I want to go to share. I want to share application, window, Chrome tab, color picker. Okay, let me know if you guys can see that. Can you see anything?
Yeah, I can see it.
Okay. So what we have here is a palette, and if you can see the crosshair moving, I can grab any pixel I want. Now notice down here, let me scroll this down. I don't know how fast this is moving, but down here I get the actual, here's the actual decimal value of each pixel. Now I was showing it to you in binary and hex, but they're showing it to you the red, the green, and the blue. They're showing it to you in decimal, but over here is a hex value for it. So you can either look at this or you can look at this hex value right here. But as I grab a pixel here, let's say I start out right here in white. If I go down and look at the hex value, there's the value of, this is the amount of red, green, and blue to make the color you see in this pixel. And let me see if I can get this on the screen together. Now I'm going to move this. Now watch what happens to the numbers right here. So as I adjust the amount of red, green, and blue, you see the numbers changes, and you can see right here the color you're getting, and the correspondence between the color, the actual decimal code over here on the right, and the hexadecimal code over here on the left. Watch what happens as I go. I'm going to go straight down to a darker color. So I've got this gray right here, and look at the values that I'm at now. Now I'm going to, now watch over here as I go across. I can vary the amount of red, green, and blue, and I'm going to just move this out kind of at a diagonal, and you'll see that now, depending on, see I'm getting more red in there now. I'm going more towards red, but the green and the blue are kind of staying the same. So you can move this around and get almost any color in the rainbow. But to see what's actually stored for each pixel, you have to take the number 89, convert it to binary, take the number 69, convert it to binary, and for the blue, take the number 69 and convert it to binary. And that would be the binary value stored for that particular pixel to represent the color that that pixel is representing. So this is a really good thing. This is just a, I don't know what they call it, a color picker, red ketchup color picker, but you can play around with this and get an idea between the the pixels, the actual colors, and then the hexadecimal code to represent those colors. All right, anybody have any questions or comments?
I have a question about the homework, our last one.
Okay, let me get out of here. So web designers use this application. They can actually go in, find the color they want, and then down here where it says HTML, they can actually put this on their web page, and then they can get this color right here exactly. They can use that to match a color. So okay, let me get out of this and let me stop sharing. I want to go off of this. I want to get off of this. Okay. Are you guys, can you hear me now, see me? Am I back?
Yeah.
Okay. All right. So you have a question over the homework?
Yeah, I got a little confused by the two's
Hold on a
complement.
second. I cannot hear you. Go ahead. Say something.
Okay, so
That's too loud. All right. Which homework are we talking about?
so it's homework 3,
Okay.
and it was number 3. It was the two's complement, subtraction by addition.
Do you have it in front of you?
Yeah.
Okay. Can you tell me? I don't have it at homework. Can you just tell me the problem?
Okay, so it says do letters C and D from.
Just pick any one. It doesn't matter.
Okay, so the numbers, it's 1110
1110
minus 011. Yeah, and then they wanted to take the two's complement of, I guess, the bottom number and add it and still get the same answer.
Yeah. Okay.
I was able to get the right answer, but at first I didn't have that leading 0, so
Yeah.
I ended up with 0, 1.
Yeah. So that's the thing. Remember that you really can't write a number like this, and that's why we spend so much time talking about registers and bits and bytes. These numbers have to go somewhere. They have to. If I'm going to add them, no matter how I do the addition, two's complement or whatever, subtraction, I got to store these numbers somewhere. So this number right here would be in the register. So I would have at least a 4-bit register, probably like an 8-bit register, but I have all leading zeros. But since these are 4 bits, let's just do 4. So I have this register right here, and I would have this register right here. In that top register, you would have this number, 1110 base 2. And then the bottom one, you'd have this number, but you can't just put in 011 like that. You can't not have something in the register. It's got to be something there. If you put it there, it's called data. If it was already there, we call it garbage. But we don't want garbage in our register. So you got to put that leading 0. So if you try to do the two's complement on this number, it won't work. You got to put the 0 there, and there's really one there, even though I didn't write it. You got to have the number of bits have to match up. And then after that, it should work out. So if you're going to do this, you say, you got 1110. When I take the two's complement of this, I really want to take the two's complement of this. So up to and including the first one, I'm going to leave it alone. Everything after that, I'm going to change. This is a 0. This is a 1. This is a 1. So now I'm going to add 1101. I'm changing this from subtraction to addition because I'm adding the opposite. So then you should add this and 1 here, get a 1 there. A 1 and a 1 is a 0, carry 1. A 1 and a 1 is a 0, carry 1. So this is a carry. Then I got that 0 and the 1 right there. And so then I just discard that one. So I should get a 1011 base 2 if I did it right. Is that what you got?
Yeah, that's what I got.
So I think, but you raise a fair point. You raise a fair point. There should have been a 0 here. And if you try on the 3-bit number, it won't work. When you're doing this two's complement, the machine is actually using shift registers to hold the numbers, and then the logic is doing the actual math. So you got to have the same number of cells in the register, which means it translates to the numbers you're adding or subtracting have to have the same number of binary digits in it. So that's a good point.
Okay, thanks. And can you remind me why we throw out that carried 1?
It's just a rule. Just throw it out.
So once you get
I don't know
4,
mathematically the scientific principle behind it because I didn't spend that much time. But yeah, when you have a carry, you just discard it. If you do regular subtraction, you'll see you just get this part with no carry. So in one's complement, I haven't really looked at it deep enough to figure out why we get that carry, but I just know to tell you that when you have a carry, you just throw it out. So I don't have a reason for you.
Okay, and is that just at the end?
Yeah,
Or is it?
at the leftmost bit when you have a carry, you discard it.
Okay, great. Thanks a lot.
Good question. Anybody else have a question?
I have a question. I emailed you yesterday. You probably didn't see it yet. I'm trying to order the lab manual, so I have it because we're
Yep.
probably gonna need it soon. And I remember in class you showed us the cover of it, so that we make sure we get the right one. Can you
Yeah.
post that or send it to me? Because I was looking for it and I don't think it's
Oh, it's
posted.
on the
Is it in a PowerPoint or something?
No. Are you able to get online now? Or are you?
Yeah,
online?
I can look on Canvas right now.
Yeah, go ahead and bring that up, and I'll just wait right here while you do it. Are you able to keep me on here and do that at the same time?
Yeah,
Okay, bring that up and let me know when you logged onto our Canvas.
I'm on Canvas right now and I have like modules pulled up.
Now go to the home page.
Home.
Yeah, that's the one where all the
The picture of lab manual. Okay, cool. All right.
you see it? Okay.
Yeah, I see it. Thank you.
I forgot. I think I told you guys I would email it. I put the link there and forgot to tell you about it. That was my fault.
Okay. Thank
So
you.
yeah. Okay. Thank you. Anybody else? You guys really ask good questions. I love this. Makes my job more fun. The students are involved like that. I don't mind doing the class. So, well, I have a dog that I had, it's a pit bull. She had tumors developed. So back in, I don't know, operation, she had an operation in April. I think I spent like $3,000 on this surgery. And then the tumors came back, I guess about 2 weeks ago. And then her legs swole up. So I got a 6 o'clock appointment at the vet, and I know what they're going to tell me, that I got to put her to sleep. So that's kind of sad. I feel so bad right now because I go home and she looks at me and I'm thinking, well, my appointment is at 6 o'clock today, and by 7 o'clock she might not be around anymore. So you ever had to put a dog down and you know how that feels. But anyway, that's not your problem, that's mine. So guys, have a great rest of the day. Need anything, send me a text. Try to text me and not email me if you want me to get it right away. And I'll see you guys on Friday.